Okay, let's check out this peninsula off the coast of Chile. It's got a quite interesting shape here where it looks like there's kind of a shallow cataract feature on both sides. Kind of reminds me of what we find on the north coast of Algeria. And off of this shallow cataract feature, we also find sediment lobes that indicate an inland current direction. That kind of comes around, probably comes out of this cove here. And we can see other sediment lobes here, also giving it kind of an inland kind of cross shore direction. And this is North Algeria on, this is the Mediterranean. Now, this is the Pacific, and this is on Chile's coastline. So let's see if we can find any features that are interesting. So one of the first things we notice is we kind of see some ravines here, kind of a V shape here. But I really like this double cataract feature here. It's kind of a shallower cataract. I mean, it's actually pretty deep, but when you zoom in, you find that there's also ripples to confirm the idea of a fluid washing through this area. Right, here's kind of another double cataract, smaller one, intermediate ridge, and then you can go down and see more ripples. And this whole area is covered in ripples. So that gives us indication of a water current that goes, and then it goes into these ravines here. So let's just go back to the shallow cataract formation and compare that to what we would find in the central Washington basin. So this is the textbook example. This is potholes coulee. Coulee and cataract are basically the same thing, but water flowed off of this cliff edge. So you get these sudden ravines from the water current, and then when it breaks through the cliff edge, this was eroded backwards, so it started here as a U shape and moved all the way back to where this U shape is all the way back here, and then it stopped. And it's no longer forming today. And these lakes here are called plunge pools from the downward force of the water. Okay. So that's just our brief explanation of a cataract. And here we find the same thing, the double cataract feature. Doesn't have an intermediary because that got washed away. But let's look at the width and compare it to the one in Washington. Feet, miles. 1.15 miles. So that's a decent little cataract feature, and I was measuring both of them. And then let's do a little comparison. Miles, 1.47 at its widest point. So this feature actually looks maybe a little bit deeper. Let's check the 400. It's about 110 meters thick or deep. And this 150 to, this is about 40 meters. So it's not as deep, but it's still a very impressive feature. And we also find streamlined features as well. So when we go down here and we look at all these sweet ripples and the really cool river channels, you can see river channels full of ripples. And we keep going, and now we find some streamlined features. This guy is streamlined. So just imagine a water current washing right through there. And then those are obviously ripples from a water current. Wind doesn't make nice ripples like that, but the real thing wind doesn't make are river channels. So when you find river channels that curve and are rutted out, you know for a fact that that wasn't the wind. So a lot of people who are skeptical of my videos like to point out that, oh, wind can move sand and stuff. But these features are also correlated with river ruts. So that's how you know. And obviously the cataract wasn't eroded by the wind. So when, for example, this feature in Idaho is an insane feature of sediment lobes being pushed uphill, right? And this feature baffled me for a long time. But this wasn't made by wind. This was actually made by a water current. Just like the drumlins here were also not made by a water current. And the sediment lobes all over the area. I think these sediment lobes here. Okay, these are not a feature of the wind, but rather of a water current. So this is Afghanistan. We have a streamlined feature here. This mound, or this little mountain, collected all of this sand and was pushed around, and then downstream you can see there's not as much sand. And then when you go farther down, you find massive ripples. Okay, let's check the wavelength. Yeah, almost a mile, so 1,000 feet short of a mile. So this is not something a wind is going to create. Let's go to this spot here. So this is in Africa, Africa's west coast. You get the massive ripples. You get the drumlin features showing the current direction. It went parallel with the current direction while the ripples go horizontal. Very fundamental. But when you try to say, oh, that all of this was just created by the wind, even though they're such well-defined and massive features, even correlated with salt pans, the reason why you can't say that they have anything to do with the wind is because of their river channels that lead into them, right? These were not created by the wind. So that's kind of the big way to rebut the idea of, oh, all of these crazy features were carved by the wind. So we know that these drumlins are parallel features, but when you get parallel rock cuts, right, these are something I would call river scratches or current ruts, and they even can curve like current ruts and have streamlines. So this is very directional. We can understand that it went up screen, and we can see how this is streamlined. And then does that mean all of these are terraces? That's exactly what it means. It's not differential erosion. That's another rebuttal, but look at how they're all streamlined. Okay. So now let's go to, so now we're back in Chile. We understand that the water current washed over this. But the reason why I told you that and showed you the other spots is so that I can show you something that's really going to blow your mind. Now we're up in Peru. Now just take a look at this coastline. See how all this sediment's been pushed uphill? It's literally showing that it's been pushed uphill with these features. Sediment lobes going straight uphill. All of these features confused me for so long. Right here you get some streamlined features, some streamlined triangles. In the current direction, it's showing it's swept right up here. Makes no sense. How can this be the case? Well, it just is. Sometimes in science you have to look at the data first and then make the theory, not the other way around. Um, and sometimes that causes us to scrap a lot of ideas that we've held for a long time. But yeah, this entire landscape is very incredible. And you can see that you get some current ruts. Look at how they kind of fan out. Sediment lobe kind of fans out, sweeps around. All this sediment was deposited underwater too. And it's washed uphill, right? There's a spot in, I don't have it loaded, but there's a spot in North America where it's just pushed right up against the Sierra Nevadas, or rather the Rockies. And then look at this. Just look at this. Now, it's very easy to say, oh, well, this was all from the wind, but such large and distinct features weren't made by the wind. And the ruts, the current canyons, and the marine terraces were made by the ocean current. Right? Wind can't make an ocean terrace. And then we see the water washed over this. Made some nice ripples. Check the wavelength. 200 feet, not bad. But you're probably still skeptical, probably still think it's from the wind. That's okay, I got more to show you. Just hang on. Just going to keep going up the coast. I'm going to find some nice ruts to show you that this was made by a water current and not the wind. Looks like we find some mounds here. Here we've got some more sediment lobes indicating an inland direction, straight inland. Quite bizarre. So when we look at this, we actually see how it curves. Kind of reminds me of Turkmenistan. The way we get a really nice swirl to it. Look at the curve on this. And then when we zoom in, we get the drumlin and ripple combinations. Just like what we find in Africa. Yeah, I'll show you Africa. So just like we have the drumlins perpendicular to the ripples. All right, this is a good spot. Drumlins, ripples perfectly perpendicular. Same thing here. Drumlins, ripples. Let's get a nice little wavelength on it. Kind of turned at an angle, but 700. Pretty decent. This is kind of harder to see, but we still get some drumlins. Here you can kind of see them. Get the ripples. All showing an inland current direction. Yeah, look at this. It's just all going uphill. Water's supposed to go downhill. Yes, but ocean has a lot of inertia. And stuff can form deep underwater. So just because it had to have formed underwater doesn't tell us if it was 10 feet underwater, 100 feet underwater, right? 1,000 feet underwater, we don't know. So it's more scientific to keep our options open. And I kind of lean towards a sheet water flow where you've got tidal surges and hundreds of feet deep. But if you study the erosion of Earth, you see a lot of erosion where it goes back and forth, such as what we find in the Washington Basin. And that's a characteristic of what the ocean does with a tidal sequence. So that makes perfect sense for that. Here we get a nice streamlined feature around this. Trying to find some good ruts. I mean, my first example when we were in Chile was the best example of the ruts, but I know I can find some more. Yeah, I mean, these features of streamlined ripples are just so cool. And then we get the little ripples here in these channels. So why would the wind choose to coalesce into these tight patterns? Right, that seems like something, obviously a river, sheet water flow, as it decreases, it turns into a river. That's a thinner stream, so that explains why you would get these parallel channels. Right, and this kind of reminds me of Saudi Arabia. Oh man, this is pretty sweet. Okay, here we go. See, now this is a rock layer. This is just like, or is that a lake? Hold on. I don't know if that's a lake or not. Let's see. Not sure if that's high elevation or low elevation, but yeah, it could be a scour actually, parallel scours. But if that was streamlined rock, that would verify what I'm saying. But actually, you know what? Wind can't do this either. So let's say this is a lake. Wind can't dig out a trough like this, right? Wind can't make parallel ruts. Okay, only water can do that. Here's a great example of some real strong accretion ridges. Right, imagine a storm making these nice berms. And then we got this feature here washed over it. So this gives us a sequence of events, right? If these accretion ridges are underneath these sediment lobes, right, we don't see the ridge continue, then that's telling us this happened after the ridges, the law of superposition. So that's pretty interesting. Here's another example of some nice accretion ridges. Yeah, so this is something wind isn't going to want to make such a tight, clean pattern. And nor is wind responsible for these accretion ridges. And then you get all the way down to the shore and you find the same features. You know, really trying to indicate that it was from the ocean. Because the accretion ridges and all the other features are so seamless. Yeah, these are really clean ones. Right in line with these big sediment lobes. And this is a pretty lush area, so the more lush it is, the harder it is for wind to move stuff. And then this spot in Peru is so cool. This is one of the biggest streamlined features. And just the cleanest too. .3 miles wide. And then you got another one here. And you've got them all over the place. And they're just so clean. Now here's the thing. Look at this. This is a cataract feature. That's what I was looking for. Something to prove that it can't be wind. Because the wind, how deep is this? Maybe like 10 or so feet. Let's check. 13 meters to 7 meters. 6 meters. So that's like 25 feet difference. So this being a shallow cataract feature, you get 25 feet. Imagine getting a shovel and trying to remove 25 feet throughout this whole area all the way down. That's a lot of work in the physics sense of the word. Work, energy, all that. It takes a lot of force to remove that rock. It's not going to be wind to do that, nor is it wind that shaped this big arcing streamlined ripple. So that's how these were formed. First they were formed as a ripple and then they became streamlined. There's locations that make that really obvious, but a lot of times we find them stand alone. But yeah, these spots are sick. Then we kind of get into a little bit of a salt scablands area. Right, that's indicating ocean current, which is the big theory for all the erosion on Earth. The real answer, it was the ocean. Anything that's a geologic mystery, for example, mounds, why there's drumlins in the equator, why there's eskers in the equator, all manner of mysteries. A lot of them have the answer of being formed from the ocean current. Megascale ripples, megascale rivers. They're all very highly correlated with salt scablands. Now look at these accretion ridges going all the way up continuously to 85 meters up. So that was a lot of ocean currents wrapping and wrapping and wrapping around. Now the law of superposition with accretion ridges is, for example, with marine terraces, the higher altitude is first. So they came down through here and towards the core, towards the inside, towards the ocean. And then they kind of seamlessly fit with this marine terrace here, which was also made by the ocean current. This marine terrace looks kind of sick. It's got some parallel ruts in it. That's letting us know that the power of the ocean current that formed the accretion ridges was also powerful enough to make parallel ruts in the rock. So yeah, it's a lot of evidence. And oh yeah, nice canyon here. Let's check out this cataract. 0.6 miles. Not bad. I mean, that's a real nice one, really. All of these canyons here. Terrace, parallel ravines, sediment lobes. They just keep going. South America's got to be one of the craziest spots. All right, thank you guys for watching, and I'll see you next time. And this was streamlined by water too. Big old expansion bar. Okay, thank you guys for watching, and I'll see you next time. Bye.